Okay, let's talk about something that sounds like it's straight out of Harry Potter. Mimblewimble. Seriously, what a name, right? But what it does is even crazier. Imagine making a payment that's totally secret, completely untraceable, but at the same time, everyone can agree it's 100% valid. Sounds like a magic trick, doesn't it? Well, today we're going to pull back the curtain and show you exactly how it works.
So this really is the core puzzle, the big question we're trying to answer. How on earth can you prove a transaction is totally legit if you keep all the important stuff secret? We're talking about the amounts, the sender, the receiver, all of it hidden. It feels like it should be impossible, right? But that's the whole point. Mimblewimble is designed to solve this exact problem.
All right, so to really get how this all works, we first need to understand the challenge. Let's call it the privacy puzzle. So, look, we're all familiar with basic encryption, right? You use it every single day. You take some data, maybe an email or a message, use a key to scramble it up, and boom, it's just gibberish to anyone else. Only the person with the right key can unscramble it. It's simple, it's effective, and it's pretty much the bedrock of online privacy. But what if you could do math on that scrambled data without ever unscrambling it? Think about that for a second. Actually performing calculations on information that's still completely encrypted. This is where things get really interesting. It's a huge conceptual leap, and it's the secret sauce that makes the whole thing possible. Okay, so this special kind of math is our secret ingredient. Let's dive into how you can actually have math that hides money.
You know, the easiest way to wrap your head around this is with an analogy. Picture two locked boxes. Each box has some money inside, but you don't know how much. And each one is locked with a totally different key. You have no way of seeing what's inside. Now, using this, let's call it magic math, you can take those two locked boxes and mathematically combine them into a third locked box. And here's the wild part. This new box contains the exact total amount of money from the first two, and you did it all without ever opening them, without ever knowing the amounts inside. Pretty cool, huh?
Okay, so for those who like the math, here's the rule that makes this trick work. Adding two encrypted things together gives you the exact same result as if you added the original amounts first and then encrypted the total. The new key is just the sum of the old keys. It's this simple, really elegant property that is the engine behind absolutely everything in Mimblewimble. Okay, so we've got this really cool mathematical tool, but how do we actually apply it to a real-world transaction to make sure everything adds up correctly? Well, that brings us to our next step, balancing secret transactions. Rule number one of any financial system, right? You can't just create money out of thin air. The amount of money going into a transaction has to be the exact same as the amount coming out. Inputs have to equal outputs. And with our magic math, we can prove this is true even when all those amounts are totally hidden inside their locked boxes. But we've hit a snag, a complication. While the amounts in our locked boxes balance out perfectly, the keys we use to lock them, they don't. The sum of the input keys doesn't equal the sum of the output keys, and that little imbalance throws the whole equation off. Technically, as it stands, the transaction isn't valid. So we've got a problem. So here's the next challenge for us. How do we get those keys to balance out just like the amounts did? And this is the tricky part. We have to do it without revealing a single thing about those secret keys. How in the world do we pull that off? Well, the solution is actually really clever. It's an elegant little fix that adds one new piece to our transaction. This is what we call the kernel's clever trick. The system introduces this thing called a kernel. The easiest way to think about it is like a special token, a token that is mathematically guaranteed to be worth exactly zero. It's not real money. Its one and only job is to be a balancing tool for our equation. So the secret key for this zero-value kernel, it's custom built to be the exact missing piece of our puzzle. It is literally calculated to be the difference between the output keys and the input keys. And think about it. Only the person making the transaction could possibly know this number, because they're the only one who knows all the original secret keys in the first place.
And just like that, once you add the kernel into the mix, everything lines up perfectly. The secret amounts balance, and now the secret keys balance too. The math checks out, we're almost there. But there's one last step. How do we prove to everyone else that we did all this correctly without giving up any of our secrets?
This is it, the final piece of the puzzle. The step that proves our whole magic trick is legitimate. This is the ultimate proof. Okay, so remember, in any cryptocurrency, to spend your coins, you have to prove you own them. And you do that by proving you know the secret keys. Mimblewimble is no different.
It has to do the same thing, but with that extra layer of difficulty. You have to prove it without actually showing anyone the keys. This is the final test. And the answer, once again, lies with our clever little kernel. The person who created the transaction creates a digital signature on the kernel. And this one signature, this single piece of data, proves everything all at once. It proves the kernel is worth 0, which means no money was magically created. It proves the creator knows the kernel's secret key. And if they know that key, it indirectly proves they knew all the other input and output keys too. It's a brilliant, all-in-one proof that keeps all the secrets safe.
You know, the source material puts it perfectly. It says the kernel acts like a public key, and signing it proves that no value was created or destroyed. What that means is that the math of the signature only works if that kernel's value is 0. And if the thing you use to balance the equation is worth 0, well, that's mathematical proof that the inputs and outputs had to be equal from the start.
And that's it. That's the whole trick. The amounts are hidden, the keys are hidden, but the transaction is mathematically, undeniably proven to be valid. We know the sender had the funds, and we know no money was created out of thin air. All of that proof with total privacy.
So, what are the big takeaways here? We've just seen a method that lets you verify something is correct without ever seeing the secret data itself. Think about the implications. This is huge, not just for cryptocurrencies, but for any system where you need both proof and privacy. So the final question is, now that we know this kind of magic math is possible, what else could we build with it? It really gets you thinking, doesn't it? Thanks for diving into this with us today.